Okay, so chapter 4 was all about forces, and now we're going to Newton's laws, and chapter 5 is about applying them. And this chapter is going to be broken up into 3 different videos. The first section talks about what's called equilibrium. Okay, when an object's at rest, it's in what's called a static equilibrium. So the forces are all balanced out. Dynamic equilibrium is when an object's moving at a constant speed in a straight line. Okay, in both those cases, there is no net force. So, kind of goes along with Newton's first law of motion. Objects that have balanced forces on them have a constant state of motion. So we have this: if an object is in equilibrium, we can use Newton's second law to figure out the forces that keep it in the equilibrium. Okay. So if we look at this thing, an orangutan weighing 500 newtons hangs from a vertical rope. What's the tension of the rope? Okay, so if we know the weight of the orangutan, the force tension has to balance out. So the orangutan is at rest, so it is in a state of equilibrium. The net force on it must be 0. So the tension and the weight must be equal to each other. So the net force is 0. Okay. All right. So this should not come as a shock, because if you're only having one rope holding the orangutan up, the force of tension is going to equal the weight of the orangutan to keep it at a net force of 0. All right. So a rod is free to slide on a frictionless sheet of ice. On one end, the rod is lifted by a string. If the rod is at rest, which diagram shows the correct angle of the string? Okay, so if you think about what's going on here, okay, we would essentially get an area. So we have to look at this. Okay, so we have to identify the forces going on. All right, so if the rod is to hang motionless, it's got to have a static equilibrium of 0. So the 3 different strings can have free body diagrams drawn like this. Okay, so for A, the one that's at an angle to the left here, the tension is there, normal is up, weight is down, force net is this way, because we have some left moving friction there, or force there. When it's lifted straight up, we have tension, and we have the normal force, and we have the weight going down. When it's to the right, we have a net force to the right. Okay, so tension always acts along the direction of the string, and that the weight force always goes straight down. Okay, the ice is going to push up with a normal force perpendicular to the surface. So if the string is angled, we can see that there's going to be a horizontal component. Okay, so for A and C, there's a horizontal component of that force, which means that the object's going to move. Okay, B is the only one that has the 2 upward forces eliminated by the downward force and no left or right force. Okay. All right, so another one here. So a car with a mass of 1,500 kilograms is being towed by a steady speed by a rope that's held at a 20-degree angle. The friction force of 320 Newton force opposes the motion. We need to find the tension of the rope. So we know that the rope is being lifted at an angle of 20 degrees. We know the mass of the car, 1,500 kilograms. And we know the friction force of 320 newtons. So ultimately, we're going to use that to figure out the tension of the rope. And it says the car is being moved at a steady speed. So because of that, because the car is being moved at a steady speed, there's no net force acting on this object. Okay, so we look at what's going on here. We have a friction force. We have the weight force, mass times acceleration due to gravity. We have the normal force, the force lifting pushing up from the ground, and the tension. Okay. So we know the x components of the forces and the y components must be 0, okay, because it's moving at a steady speed. Okay, so now we start rearranging things to look at the x and y components of the force. So the normal force has an x component. The normal force, the value is 0. The y component, there's no x component for normal force. The y component of the normal force is all the normal force pushing up from the ground. The tension has an x component, has a y component. Now we're going to have to use the trig functions cosine and sine to figure out the value of the x and y components. The friction, okay, and then we have some other force applied by the tension. All right, so Newton's second law, we can put in terms of this. Okay, so tension is F divided by the cosine of theta to get 320 newtons. Okay, the first equation. We know the angle. Okay. So because we know the angle and we can figure out the x and y components, okay. Right? So tension on the rope up instead of the forward direction. We need to know a little bit more tension. There needs to be a little more tension on the rope than the weight of the car. All right. So we have this problem as well. 100 kilogram block with a weight of 980 newtons hangs from a rope. Find the tension in the rope if the block is stationary and if it's moving upward at a steady speed of 5 meters per second. Okay. So if it's stationary, the tension is going to equal the weight of the rope. Okay. The weight of 900 newtons hangs on a rope. Okay. Because it's hanging stationary, the tension of the rope needs to be 980. Okay. If it's moving upward at a steady speed, again, no net force. So that force also has to be 980 newtons. Okay, moving on to Newton's the second law. Okay, so again, dynamics, now we're moving. Things are accelerating. So the force is acting on an object can be determined by acceleration, the net force divided by mass. Okay, so if you have a net force now, the object's going to accelerate. It's going to gain speed. Its rate of change of speed is going to actually be there. All right, so let's look at this in terms of math and figure out what we can determine here. So we have a golfer that puts a 46-gram ball with a speed of 3 meters per second. Friction exerts a 0.02 Newton force that slows it down. Okay, we're going to figure out what the putt will be 10 meters away. Okay, will it reach that far? So ultimately, you have to figure out how far it's going to go. When we know the mass, we know the initial speed, we know the friction force, and we need to figure out when the speed is 0, how far does it go? Okay. So it starts at a 0 position with an initial speed of 3 meters per second. It's going to go to 0. That's the final speed. We know the force applied to slow it down to apply that acceleration. And we know the mass. So look at what's going on here. We have a negative acceleration because it's slowing down. It's a constant negative acceleration because the force applied is constant. Okay, so now if we look at the free body diagram here, we have the friction applied, the normal force, the weight force, and the net force now is backwards because the ball isn't going up or down. All right, so again, our total net force for in the vertical is 0, but in the x there is an acceleration. Okay, we have to take the normal force the normal force x component, which is 0. We do have a force applied. We know that force. This is the weight, the horizontal portion of the weight, which is 0. Okay. So we know this F. Because we know the F, we can figure out the acceleration because we know mass. Okay. But we have to figure out these net forces first. This one's relatively easy, but other ones we're going to need to look at more information. All right. So we know that the net force is 0.02 newtons, and it's negative because it's slowing it down. We know the mass, so acceleration is force divided by mass. Negative 0.02 newtons divided by 0.046 kilograms gives us our acceleration of negative 0.435 meters per second squared. Okay, it's to the left for acceleration. Now we need to figure out time. For that, we can use, actually we need to figure out distance. We can figure out with their acceleration, we can figure out our final distance. Okay, we know we can use this one, the x final equals x initial plus vf squared, and actually this starts off as the vf squared equation right here. And we work it around to get 10.3 meters. And so if they do this, if she does this right, if it goes straight, the ball will be in the hole. Okay, very similar problems will be done with like this in class. Very similar problems will be asked you like this on the AP exam. Okay, so again, we have a car, 1,500 kilogram car, with a friction force of 320 newtons. What's the tension of the rope if it goes from rest to 12 meters per second in 10 seconds? So now we have an acceleration. Okay. So now instead of like the previous problem that we had with the towing, this one has an acceleration. Okay, we know the force of friction. We know the normal force. We know the weight. There is a net force in that direction. And we have this force of tension that we need to find. So ultimately what we have to do is we have to figure out this net force because we know the mass of the car. So once we figure out this net force going in this direction, we have net force, we have mass, we can figure out its acceleration. Okay, so again, figure out the net forces. We know to get the net force, we have to look at our acceleration. We know that we went from rest to 12 meters per second in 10 seconds. So 12 divided by 10 is 1.2 meters per second squared is your acceleration. That's your rate of acceleration. Okay, then we use that. Now that we know our acceleration, we know that the tension, if we're going to figure out the x component, okay, since we're looking at the cosine of theta, and go back and look at the chart here. So cosine of theta is we're looking at this. Okay. All right. We know our acceleration. So we know that the tension is 2,300 newtons for the force. Okay. So tension is mass times acceleration, the horizontal distance, which we know, plus the force of friction divided by the cosine of 20 is 2,300 newtons. Okay. All right. So now this one has an acceleration this time. Okay, 100 gram block with a weight of 980 newtons hangs on a rope. Find the tension in the rope if the block is accelerating upwards at 5 meters per second squared. So now we know the acceleration. Okay. If we know the acceleration, we know the mass of the object. So mass times acceleration can get you the net force. Okay, so if you think about that, mass 100 kilograms times acceleration of 5 meters per second is 500 newtons. So that means the tension has to be 500 newtons more than the downward 980 newtons. So the tension upward actually has to be 14,980. Okay, 500 newtons more than the tension because we have an upward acceleration. Okay, we have a downward weight. The tension up has to create this acceleration, so it has to be more than the 980. Okay. So again, more sample problems for you to look at. Okay, we can look at this. We can find the tension on this rope. We know the weight of the object. If we know the weight of the object and we know how this angle is, we can find the tension. Because if you know this component is 50 newtons, you know 20 degrees. So the vertical component of a right triangle is 50 newtons. You can figure out this leg of the triangle here when you know the angle is 20 newtons. Okay. This one, another acceleration problem. Okay. You know the initial speed, you know the final speed, so you can figure out acceleration. Actually, you can solve the acceleration easily because you have, if it crosses a rough patch of snow, then exerts a friction force of 12 newtons. That's your net horizontal force. So 12 newtons divided by your 20 kilogram mass will get you your 20 kilogram mass will get you your acceleration. And then you can use the kinematics equation with acceleration. You have an initial speed, your final speed is 0. You can figure out the distance traveled. Okay, that's the end of the video. Lots of practice problems for you to look at. Consult your textbook for more problems, and we will see you in class.